Hi everyone, welcome. Today we are going to learn how to model this water supply network here by using EPANET 2.2. And before we proceed, I would like to point this out. Today's tutorial was initially recorded by Mr. Isaac Waite, as you can see here. The first version he used Microsoft hard cross method, of course with Microsoft Excel. And again, the same problem, he used the EPANET, as you can see here. And I thought maybe there are some few things I could add. So this was the essence of today's tutorial. Okay, so let's get back here. As you can see here, we have the same network, but with some few modifications. As you can see here, we have extended period simulation. Let me click run. As you can see here now, this is extended period simulation, which checks stability of our network. And not just that, there are some few modifications that I conducted. So please, I encourage you to watch until the end, because there is so much you are going to learn out of this video tutorial. That being said, I'll see you in the next part of the video. The first thing that we need to do is to change project settings. And of course, you can go here, project, then defaults. Now from here, we can start with hydraulics. Flow units, of course you can change. For me, I'm going to use liters per second. So if you prefer to use other units than metrics, you can set here. So for me, as far as I want to use metrics, then I'll set liters per second. The other thing that I need to change here is head loss formula. I'm going to use das Weisberg for the sake of this tutorial. And again, the other settings, I'll just maintain the way they are. So from here, just look on here, there is nothing we are going to change. And again, here again, junctions. So I would prefer to do this. For junction, just start with J, then keep dash. I will explain later what does this mean. And for reservoir, R, then dash, tank, ST, then dash, pipes, P, dash, then pumps, even though we don't have pumps, just PMP, valves, we don't have, just V. So these are the settings that I would prefer from here. And if you want to set default for all new projects, of course you can take this, but for me, I'll just click OK. After that, we can go here to file and check preference. Of course, there is nothing here we can change. Format, demand to decimal, there is nothing we can change here. Just leave the way there, then click OK. After that, right click and start with options. Now, links, label, notations. Here in notation, what we need to change here is to make sure that we take this display node values, and of course display link values. And again, flow arrow, you can set here whatever you want. For me, I'm going to use field. And again, notation, again here we change our font size. Of course we can change as we proceed. We'll come back, then click OK. So this is the first step, very important step. So the next step that we need to do is start by working here. So as far as our tutorial goes, we have a water system with reservoir. So we'll add here a reservoir. Then reservoir, we have this node here. And again, this one. Again, this. And this. Another node here. Of course, the other one was here. Okay, so the next things that we need to do here is to link our components. As you can see here, we have a pipe from a reservoir. We can start here from reservoir to node number to this node here, which is node A, and again here to this node, and here to this node. So do it again from here to this node here. Again, we can link with this node. Again, this one and this. Lastly, this one. Now from here, we can link here all the way to this node here. Okay, so after here, what we need to do is again to assign elevation to all our nodes. Okay, all our nodes in the reservoir. So elevation, we can start here. So reservoir, our reservoir is in 65. Click OK. Node A, or this node here, has elevation of 0, so we can leave the way it is. And node B, elevation is 9.4. Then click OK. Node C, 19.2 as elevation. And again, node D, 25.2 as elevation. And again here, node F, if I'm not mistaken, node F, 5.5 elevation. And again, this one here, elevation is 2.1. So we assign here 2.1, then done. After elevation, what follows is to assign demands on appropriate nodes. So from here, this node here has 0 demand, and again, node B here has a demand of base demand of 350 liters per second. And again, this one here, node C has no demand. And node D, here we have a demand of 100 liters per second. So if you go here to node F, we have a demand of 50 liters per second. And again, node E, here we have a demand of 450 liters per second, of course. From that, the next thing that we need to assign is we need to assign diameters and lengths on each pipe. So we'll start with this. Okay, so from reservoir to junction 1 or junction A. So here our length is 1000. Of course, that's 1000. No, our length is 10 meters, and diameter, put here 1000. Okay, so this one again, our length is 220, and diameter here is 400. This one, length is 100 length meter, then diameter is 200. Again, this pipe here, length is 80, and again diameter is 150. Okay, and here this pipe here, length is 200 and the diameter is 300. And this one, length is 80 and the diameter here we have 250 millimeters. And again, this one also we have a length of 150 as length. Then we can put here 350 millimeters diameter. Then take this one, we have length of 180 and diameter of 300. So basically that is our network, and as you can see here, we have a reservoir, these nodes here, and pipes. Of course, we assigned demands on each appropriate node. Base demand, again in this one, base demand, we have a base demand there, and also this one. So what we can do here is, of course, we can run our model to see if we have any error. I think there is somewhere something is not correct. Select pressure. You can see here maybe one length, diameter. Let's change the roughness. Now, to change the roughness, of course, what you can do here is to change one pipe by another, but to save time, you can go here to edit, then select all. After that, you can group edit. Then we need pipes. Then from pipes, you can assign roughness, which was 0.3. So from here, just click OK. So all pipes here are assigned with 0.3 as roughness. Of course, our formula is das Westberg 0.3. Run again. Okay, now we are done. So from here, now let's look here clearly. As you can see here, this is our reservoir, and this is a pipe from reservoir, and this is point A, which is, for me, I just named it as junction 1, which is point A, literally. This is point B, C, D, F, and E. Okay, so you can see here water from here goes this way, and it rotates like that. So we need to display pressure here. Of course, you can go to this browser here, then click map. You can see on nodes, what we want to display is pressure. So this is what we have. Then from that, on links, what do we want to display? Of course, you can display anything from this. So for me, I'm going to display flow. Okay, so you can see here from reservoir, we have a total flow of 950 liters per second, and at this pipe here, from point A to point B, junction 1 to 2, we have a total discharge of 528.11 liters per second, and the other pipes as well. Okay, so to display the pressure, you can just go to data, then map, and select on nodes what do you want to display, then click pressure. You can even display elevation if you want. So for me, and for the sake of this tutorial, then we can display pressure. Okay, links, of course you can display even velocity, but for the sake of this tutorial, we display flow. So this is what we have. Now before we proceed, as you can see here, we have a total flow here of 950, but one thing here you need to notice is that we have a negative flow, and again here is a negative flow, and also here is a negative flow. So to remove the negative values, what we need to do is to actually right click this pipe, just right click and click reverse. Okay, again this one, click reverse, and also this one, click reverse. So from here, again even this one, just click reverse. So from here, just run. So there is no so we don't have negative value anymore. Now as you can see here, you have a text font height here is a bit small. What we can do here is actually to click right click, then go to options, right click, then click option. So from here, go to notation. Okay, go to notation. So from notation, font size you can even put 9 or 10. So for me, I'll keep 10. Then click OK. At least now our font size is a bit big, so as you can see clearly. And one thing again we need to do is to display this node ID here. So just right click option and go to notation, then display node ID and even pipe or link ID like that, then click OK. So you can see here you have junction 1, 2, 3, 4, 5, 6. Okay, so here is junction A, B, C, D, E, F. That is it. So what we need to do now is to compare the calculated value or value that was calculated with Excel and the value that we calculated with EPANET. Now as you can see here, I have Excel sheet here which I put the value. As you can see here, these are the value calculated by Excel, of course by Mr. Isaac Wade. And here I need to put my EPANET values. So what we need to do here, now bear with me a little bit. Okay, I need to see, yeah, just like that. So from here at junction A, as you can see here, junction 1 for me is junction A. The value that we got here was is 64.99, and again B, junction 2, which is B, 46.37, and C is 18.55, and the point D, node D actually, is 15.53. Node E, which is this one, J6, is 33.51. And lastly, junction 5, which is this, 37.85. So that is it. Okay, that is it. So this is the calculated value, and these ones are values that we obtained from EPANET. So this is Excel with hard cross, and this is EPANET. Now let's compare here. As you can see here, this is calculated value EPANET, of course by using das Westbag, and you can see here error. This is the error, and again this is percentage error. So for me, I see the error is quite small. Okay, it's quite small. As you can see here, is only negative 0.01, negative 0, positive 0.37. It's quite small. Okay, so that is it. So this is by using hard cross, and this by using EPANET with that Westbag. So that is it. But one thing here I need to add. One thing I need to add. Now from this, let's get back here. Let's get back here a little bit. Now let's assume this one is a water supply project. Okay, water supply project. You have here a reservoir. It can be a river, or it can be a dam. Of course, a reservoir, that's a dam. And here you have a community of people, and our system is supposed to supply this water here to the community. As you can see here, as you can observe here, one thing that we need to keep it in mind is that any water supply project need to have a certain range of parameters like velocity, like unit head losses. Again, we need to have pressure at certain level. So as far as pressure goes, I think there is no problem. But we need to go further and investigate what is the value of velocity that we have in our system. Okay, and we need also to check if the value is within acceptable range or not. We can even go further to check unit head loss. Of course, per 1 kilometer, what losses do we have? How many meters of losses do we have? So this is what we are going to do now. Now, as you can see here, remember from browser, just click map, then let's click flow and velocity. Now take a look at here. You have 5 liters per second, 5 meters per second, sorry, as velocity. And as you can see here, you have again here 5.67 meters per second. Now a typical water supply project is supposed to have at least 0.5 meters per second to 1.5 or 2, depending on country, but for me at least 1.5 meter per second. But as you can see here, we have very huge velocities up to 5. Now we need to find a way to modify this, at least to make sure that our velocity is within those ranges, 0.5 to 1.5 meters per second. Now let's ask ourselves, why do we have this amount of velocities here? Now before we go to that, let's again check unit head losses. As you can see here, we have 42, we have here 120 meters per kilometers, but it is advised to have at least 10 meters of head losses per 1 kilometers. Okay, 10 meter of head losses per 1 kilometer, at least within that area. So as you can see here, we have 120 meters per kilometers. This is a very huge. Even here, as you can see here, we have 96. Here we have 42. Here we have 90. We have 180. Again, these are very huge values, and we as engineers, we need to think a little bit about this. Now let's go back here to velocity and ask ourselves, why do we have here a very big velocity, and why do we have this amount of head losses? It's simple. You have a certain Q, and that Q and your pipe is not capable of handling such a Q. So what we need here to do is at least to increase the size of our pipes. Okay, so as you can see here, you have a diameter of 400 millimeter, and of course within this diameter we have a flow of 528 liters per second. So what we need to do here is simple. Let's increase diameter, at least take it to 600 and see what do we have. Then run. Of course everything is perfect. As you can see here, this color is not good. Let me change the color. So from here, just click reverse and add here red. So from here, anything below 0.5 is not acceptable. 1 is acceptable, 1.5 is acceptable, but anything above 1.6 I can say is not acceptable. And let's change the color. Put here purple and again here purple, so as we can see clearly. Okay, so what we have here is, at least now we have 1.94. let's run again. Let's increase again now before that, let's check unit head loss. Again we have 5, is not good. Let's increase it to 800. What do we have? Run again. At least here we have 1. Let's check velocity, 1.1. Now let's go back to another pipe. I think this one. Let's change the value here. Okay, let's change the value. As you can see here, we have a pipe of 300. Let's get it to 600 and see what do we have. Then run. At 1.6 and unit head loss 4. Of course head losses are within a certain acceptable range, which is below 10 meter per kilometer. We can leave it the way it is. And let's go this pipe here, pipe 6, pipe between F and E. Double click and let's change here to 400. At least let's see what do we have. 22, not very good. 600. At least now let's check velocity. Is velocity within acceptable values? As you can see here, velocity now is within acceptable values, but here our velocity here is very small. Okay, velocity here is very small. Let's click again. This, let me get it back to 400. 3, nope. Let me put it 600, and again this reduce to 300. But this pipe here not that good. Let me check here unit head loss. Let me increase a little bit this 300, because this one takes water to this pipe. Okay, and velocity, yeah, at least now after increasing, now this pipe here supplies water to this pipe, so automatically if we increase the size of this pipe, automatically we are going to increase the diameter. If you increase the diameter, automatically you have big pressure, high pressure, which in turn going to affect this pipe here. So what can we notice here? Again, in unit head loss, yeah, unit head loss is very good, but can we change this? As you can see here, we have a velocity of 1.8. Let's take it to 700 at least. Let's see what we have. At least now, okay. Unit head losses, Unit head losses, both of them are below 10 meter per kilometer. You can see here is 0.8, 0.7. Again, this one is 2, this is 3, 4, 10. Not bad. So at least now our system is well balanced. Okay, velocity is within acceptable range, and again, unit head losses is within acceptable range. So that being said, the next step, which I believe we can improve this system, is to check its sustainability. Okay, yes, our system now has a very good velocity, and at least unit head losses, both unit head loss and velocity are within an acceptable range. But is it sustainable? Can it withstand demand fluctuations within a day? Can it supply water to our community? Now, given the water demand assigned or base demand assigned, can it supply water to the community? Okay, is our system sustainable? Now, this is what we are going to see. Now, for now, let's introduce another concept which is known as extended period simulation. This is very important. Now, this is going to test our system to make sure that it is capable of operating, or it is capable of supplying water to the community regardless of demand fluctuations within a day. Now, by starting here, we can go here to data, then click let's click patterns. Now, before patterns, let's click options and go to times. Now, our extended period simulation total duration here, we set it to 24, and again, pattern step, we can set a pattern step of 2 hours. Okay, 2 hours. You can even set 1 hour, you can set to 3 hours, but for me, I'm going with 2 hours. I think the other values you can leave the way they are, then we can close. So from here, then click patterns. Now from patterns here, just click add. Of course, just maintain the ID as 1. You can change if you prefer. So for me, I'll just maintain it the way they are. As you can see here down, it tells you time. Bracket time period is equal to 2 hours. Now, what we need to notice here, time period here starts with 1. And here we have a multiplier. Now, a multiplier, of course, these multiplier values are calculated, but for the sake of this tutorial, I want to keep it simple. Okay. Remember, we are starting here at midnight. So at midnight, of course, we expect our demand to be very low, because at midnight people are asleep. So we expect at least to have maximum 10% of our demand. So 10% in decimal place, we can put here as 0.1, which means at least 10% of our assigned demand will be consumed at that time. Okay, so from, let me bring it here, so 0 to 2 a.m. we have again 0.1. Only 10% of our demand will be consumed. Okay, so from 10 to 12, from 4 a.m. to 6 a.m. at least now we can have a little bit increment of our demand, let's say 0.5. Now from 6 to 2, at least this is the moment when people are going to school, some are going to work, so we expect our water demand here to be at least to have a high amount of demand. Now from 6 to 2 a.m., if I'm not mistaken, we expect to have the maximum value, which is at least 2. Now this 2 meaning that our demand will be doubled. So if, for example, at this node here we have 350 liters per second, we expect at this time here the amount to be doubled. Okay, so we expect to have at least 7 liters per second of demand. Now from 8 a.m., if I'm not mistaken, to 10 a.m., we expect again to have a high demand, which is 2. Okay, now from 4 to noon to noon. So we expect to have at least reduced amount, let's say 1.5. Again, from 12 all the way to now, from here let's say we have 1, so from 12 all the way to 2 p.m. we have 1. Again, maintain 1. So from 10, at least this is the time when people are coming back from school, some from work. Demand here expect to be high, so 2. Again, here we will maintain as 2. Now from 2 a.m. again to 10 a.m. demand is going to reduce a little bit. Now from 12 hours all the way to midnight, of course we can have 0.2. So this is a demand pattern that we have here. As you can see here, we have up, then up. It's like this shape here, as you can see. Now this is our demand we are going to assign in our system here. So we can click OK. So demand ID here is 1. That is very important. Now we have a few nodes. Let's say in this node here, of course you can just go select all, then assign all. Now group edit, then click junction. So from junction we need to select base demand. So within a base demand we'll put here a pattern ID which is 1. No, actually it's not base demand. Now demand pattern 1. So click here 1. So what this does is that it goes to every node and assign the pattern demand with ID 1. Okay, so as you can see here we have a 1. So in literally every node assigned with 1. Okay, so from that let's run our system again. Of course this is the most fascinating part of our tutorial. Let's run our system again and see how our system is going to behave with demand fluctuations within a day. Okay, so let's go here and click run. So it is successful. So from here, from map, select, just click here forward. Just click once and let it go and let it run. So as you can notice here, as time move, our demand here is, our flow fluctuates, even pressure fluctuates. As you can see here, just watch closely, you can see here 0.3. okay, it fluctuates just like that. So this fluctuates by taking into account our demand pattern that we assigned earlier. Okay, so if in a node, let's say we have 10 liters, it's going to take that 10 liters and multiply with multipliers that we assigned in our demand pattern. So it is just like that. So this tells us that our system is capable of supplying water to our community. But one thing here we need to notice, if we didn't change anything, possibly our system would not be able to withstand demand fluctuations within a day. So as engineers, I think it is very important to take this into account, and if possible, and if your system is expected to be consumed by within a large community, so it is very important to perform extended period simulations. Now let's go here and check flow. So this is 12, this is 6. So you can see how flow fluctuates. Okay, we have here a negative flow. Okay, as you can see here, I think this node here we can reverse, run again. Okay, click forward. So as you can see here now, okay, look at how flow fluctuates. Now from here, let's go to velocity. Again, look at how velocity fluctuates. Okay, let's go back to flow. So every demand is going to be multiplied by multipliers that we set in our demand pattern. Now that we have done, the next step is to actually produce a report. Okay, produce a report for our network. We can go here to report, then click full. After that, just let's go and find our folder. So this is my folder. Let's call it WS, just WS, then click save. Okay, then I'll go back to my folder. So it was sorry, let me do it again. So it in project full, then click WS report and see what we have here, then click save. So from here, then to the tutorial, WS project report, then click open with. Let me open with Word. So this is the report. As you can see here, we have results, let's say at midnight. So this was a demand, and this was head and pressure. Of course, as you can see here, velocity at every hour. You have velocity, you have pressure report. So this is how we produce a full report for our network. So that being said, I have another tutorial which explains how to import survey data from Excel to EPANET. It is actually a real project, so I really encourage you to go and watch that tutorial, because there is a lot of information that you are going to gain out of it. That being said, I'll see you in that tutorial. Thank you.